There's something humbling about looking up at the night sky, realizing that every star, every flicker of light, is part of a vast, uncharted story. But what if I told you some of those celestial wonders aren't just beautiful? They're downright inexplicable. Picture this: a signal from deep space, repeating at intervals so precise it feels intentional. Or an object moving so fast it shouldn't exist under our current understanding of physics. These aren't plot twists from a sci-fi novel, they're real cosmic mysteries that scientists are scrambling to unravel. And that's just the beginning. Welcome to a journey through the universe's greatest puzzles, where the rules we take for granted seem to bend or vanish entirely. In this video, we're exploring 22 celestial conundrums that defy easy explanation phenomena so strange they've left even the most brilliant astronomers scratching their heads. Some of these mysteries are decades old, others freshly discovered, but all of them share one thing in common. They challenge what we think we know about space, time, and the very fabric of reality. Whether it's rogue planets drifting without a star, or galaxies that appear older than the universe itself, each one invites us to reconsider the boundaries of human knowledge. What makes these enigmas so captivating isn't just their strangeness, it's the way they remind us how much we have yet to learn. The cosmos doesn't owe us answers, and that's what makes the pursuit so thrilling. So if you've ever stared at the night sky and felt that tug of wonder, you're in the right place. Together, we'll uncover the stories behind these cosmic anomalies, meet the scientists racing to solve them, and maybe, just maybe, catch a glimpse of how much grander the universe truly is than we ever imagined. Ready to dive in? Let's begin. On August 15, 1977, a radio telescope at Ohio State University picked up something extraordinary, a signal so intense, so unlike the usual cosmic noise, that it stunned the astronomer monitoring the data. When Jerry Amon reviewed the printout, he circled the sequence of letters and numbers representing the signal's strength and scribbled a single word in the margin: "Wow." That brief 72-second burst of radiation, originating from the direction of the constellation Sagittarius, remains one of the most tantalizing mysteries in astronomy. What made it so unusual? For starters, it matched the exact frequency scientists predicted an intelligent civilization might use for communication, a quiet spot in the radio spectrum where natural cosmic interference is minimal. The signal was also narrowband, meaning it was concentrated on one specific frequency, something rarely seen in natural cosmic phenomena. Decades of follow-up observations have turned up nothing. No repeat signal, no explanation, just that one enigmatic blip echoing across the cosmos. Some researchers argue it could have been a comet or a passing satellite, but none of those theories quite fit the data. Others wonder if it was a one-time cosmic fluke, a freak burst of energy from an unknown astrophysical event. And then, of course, there's the possibility that still lingers in the back of many minds. Could it have been a deliberate transmission, a cosmic hello from another civilization? What makes the WOW signal so compelling isn't just its mystery. It's the way it forces us to confront how little we truly understand about the universe. Even with our most advanced telescopes scanning the skies, we've never found anything quite like it again. It's a reminder that space is full of surprises, and sometimes the most profound discoveries come in the form of a single, unanswered question written in red pen on a decades-old sheet of paper. If the WOW signal left us questioning what else might be hiding in the cosmic static, dark matter takes that mystery and multiplies it across the entire universe. Picture this: every galaxy spins so fast that, by all rights, it should tear itself apart. The stars at the outer edges are moving at velocities that defy gravity's grip, unless there's something we can't see, something massive holding it all together. That invisible glue is dark matter. It doesn't emit light, absorb it, or reflect it. We only know it's there because of the way it tugs on everything else, bending the fabric of space itself. The numbers are staggering. Dark matter outweighs visible matter, the stuff that makes up planets, stars, and us by a factor of 5 to 1. It's the hidden scaffolding of the cosmos, woven through every galaxy cluster, every filament of the cosmic web. Yet, despite decades of searching, we still don't know what it's made of. Is it a sea of undiscovered particles, ghostly and intangible? Could it be primordial black holes, remnants of the universe's violent infancy? Some theorists have even suggested dark matter might be evidence of extra dimensions, leaking gravity into our reality from a hidden realm. The hunt for answers has led scientists to some of the most ingenious experiments ever devised. Deep underground, detectors wait for the rare tremor of a dark matter particle colliding with ordinary atoms. In space, telescopes map the subtle warping of starlight, tracing dark matter's gravitational fingerprints. And in supercolliders, physicists smash particles together at nearly the speed of light, hoping to create or reveal something that matches the missing puzzle piece. What's fascinating isn't just the mystery itself, but how it reshapes our understanding of reality. Dark matter isn't a minor gap in our knowledge. It's a gaping hole, forcing us to admit that most of the universe is made of something we can't even perceive. Every failed detection, every unexpected twist in the data, reminds us that the cosmos is far stranger than we've dared to imagine. And until we solve this riddle, we're like astronomers mapping a continent in the dark, aware of its vastness but blind to its true shape. Imagine a flash of energy so powerful it outshines entire galaxies, but only for a fraction of a second. Fast radio bursts are exactly that, cosmic lightning strikes, vanishing almost as quickly as they appear. First discovered in 2007, these bizarre signals pack more energy than the sun emits in 80 years into mere milliseconds. Some burst once and disappear forever, while others repeat in patterns so erratic they defy prediction. What makes them even stranger is their sheer distance. Many originate billions of light years away, meaning whatever's creating them has to be unimaginably intense to remain detectable across such vast stretches of space. One leading theory points to magnetars, highly magnetic neutron stars that occasionally unleash apocalyptic flares. In April 2020, scientists finally linked an FRB to a magnetar within our own galaxy, a breakthrough that seemed to solve the mystery. But here's the twist: most FRBs are far more energetic than anything a magnetar should produce, and their repeating patterns don't always match stellar behavior. This has led to some wilder possibilities. Could they be the afterglow of colliding neutron stars, or the death throes of evaporating black holes? Some have even speculated, though cautiously, about artificial origins like alien propulsion systems or interstellar beacons. The truth is, every time researchers think they've pinned down an explanation, a new FRB shatters their assumptions. Take the case of FRB 1211. Not only does it repeat, but its bursts arrive in a cycle lasting roughly 157 days, a rhythm with no clear cosmic counterpart. The hunt for answers has turned into a global effort, with telescopes from Australia to Chile scanning the skies for these elusive flashes. When one is detected, observatories worldwide scramble to pinpoint its origin galaxy, hoping to decode clues in its light. Yet for every step forward, the universe seems to throw another curveball. Fast radio bursts remind us that even in an age of advanced astronomy, the cosmos still holds puzzles so profound they blur the line between natural wonder and science fiction. And that's what makes them irresistible, not just as scientific riddles, but as reminders of how much wildness still lurks in the dark beyond our understanding. Among the countless stars in our galaxy, one stands out not for its brightness, but for its baffling behavior. KIC 8462852, better known as Tabby's star, flickers like a candle in the cosmic wind, except its dimming patterns make no sense. Most stars dip in brightness predictably, often because of orbiting planets passing in front. But Tabby's star doesn't play by those rules. Its light fades erratically, sometimes by as much as 22%, in irregular intervals that last days or even weeks. Imagine a light bulb that randomly dims and brightens without warning, and you'll grasp why this star has become one of astronomy's most enduring puzzles. When astronomer Tabetha Baryons first spotted these anomalies in 2015, the explanations ranged from the plausible to the extraordinary. One early theory proposed a swarm of comets, hundreds of thousands of them, circling the star in a chaotic dance that occasionally blocks its light. But comets wouldn't explain the star's long-term, gradual dimming observations showing it's grown significantly darker over the past century. Another idea involved interstellar dust, except the star's light patterns don't quite match what dust typically produces. Then came the suggestion that electrified even the most reserved scientists. Could we be seeing the shadows of an alien megastructure, like a Dyson sphere under construction? The notion wasn't entirely science fiction. In the 1960s, physicist Freeman Dyson theorized that advanced civilizations might harness a star's energy by surrounding it with solar collectors. If such a project were underway around Tabby's star, it might explain the bizarre light patterns. But while the idea captured public imagination, most astronomers remained skeptical. Nature, after all, is often stranger than fiction. Recent studies have tilted toward more mundane explanations. Observations from the Hubble Space Telescope suggest the dimming is likely caused by fine, unevenly distributed dust, possibly from shattered planets or colliding asteroids. Yet even this theory leaves gaps. Why does the dust behave so unpredictably? Why does the star's light sometimes dip sharply, then recover almost instantly? Tabby's star is a reminder that the universe loves to keep us guessing. Every time we think we've cracked its code, it throws another curveball. Whether the answer lies in cosmic debris or something far more extraordinary, one thing's certain. This star has rewritten the playbook on how we study stellar behavior. And until we solve its riddle, it remains a beacon of mystery in the vast ocean of space, a silent challenge to our understanding of how stars, and perhaps even civilizations, evolve. There's a force out there, invisible and relentless, pulling our entire galaxy along with thousands of others towards something we can't see. It's called the Great Attractor, and it's one of the most perplexing gravitational mysteries in the cosmos. Picture this: the Milky Way, Andromeda, and countless other galaxies are all racing through space at over 2 million kilometers per hour, drawn toward a point in the distant constellation Centaurus. But here's the catch: we can't get a clear look at what's tugging us in. The heart of this cosmic anomaly lies hidden behind the thick dust and stars of our own galaxy's plane, a region so obscured it's like trying to peer through a dense fog. What makes the Great Attractor so baffling isn't just its power, but the sheer scale of its influence. Astronomers first noticed its effects in the 1970s, when they mapped the motions of nearby galaxies and realized they were all streaming toward the same patch of sky. At first, they assumed it must be a massive cluster of galaxies, something with enough gravity to explain the pull. But when they looked closer, the numbers didn't add up. The visible matter in that direction, stars, gas, and galaxies, was nowhere near dense enough to account for the force at work. That could mean one thing: there's something else there, something we can't see, wielding gravity like a cosmic puppet master. One leading theory suggests the Great Attractor might be part of an even larger structure, a sprawling supercluster of galaxies anchored by a colossal knot of dark matter. In the 1980s, astronomers discovered the Laniakea supercluster, a vast web of galaxies spanning 500 million light-years, with the Great Attractor near its core. But even Laniakea might not tell the whole story. Some researchers believe the pull could be coming from something beyond it, a mind-bendingly huge concentration of mass nicknamed the Shapley Attractor, lying even deeper in space. The challenge of studying this enigma is as frustrating as it is thrilling. Because the Milky Way's own disk blocks our view, telescopes have to rely on wavelengths like infrared and radio to pierce the cosmic veil. Each new observation peels back another layer of the mystery, revealing filaments of galaxies, vast voids, and hints of structures we're only beginning to map. One thing's certain: whatever's out there isn't just a curiosity, it's a gravitational keystone, shaping the motion of galaxies on a scale we're only starting to comprehend. Perhaps the most humbling thought is this: the Great Attractor reminds us how much of the universe remains hidden, not just in space, but in plain sight. It's a cosmic reminder that even as we unravel one mystery, another looms larger, pulling us deeper into the unknown. And until we crack this gravitational riddle, we're left with a profound question: what else is out there, unseen, tugging at the strings of reality itself? The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Statistically, the numbers suggest we shouldn't be alone. Planets in habitable zones, they're everywhere, the ingredients for life scattered across the cosmos. So where is everybody? That's the heart of the Fermi Paradox, a question so simple yet so profound it's haunted scientists for decades. Physicist Enrico Fermi first posed it casually over lunch in 1950, but its implications unravel like a cosmic detective story with no clear ending. Consider the math for a moment. Even if only a tiny fraction of stars host life, the sheer scale of the universe means civilizations should be commonplace. Some should have spread across their galaxies by now, leaving traces we could detect: radio signals, megastructures, or even just the heat signatures of advanced technology. Yet our telescopes hear only silence, and our skies show no signs of visitors. This eerie absence has spawned countless theories, each more thought-provoking than the last. Maybe civilizations tend to self-destruct before reaching interstellar travel. Perhaps they're hiding, avoiding contact for reasons we can't fathom. Or could it be that space is so unimaginably vast that even the most advanced societies simply haven't had time to cross the void? One chilling possibility is the Great Filter hypothesis, a cosmic bottleneck that prevents life from progressing beyond a certain point. The filter could lie in our past, meaning the emergence of life itself is so astronomically rare that we've already beaten the odds. Or worse, it might await us in the future, a looming existential threat, like AI rebellion or environmental collapse, that dooms all civilizations before they can spread. Either way, the silence of the universe suddenly feels a lot more ominous. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but deliberately avoid contact, treating Earth like a nature preserve. It's a concept that blends science with philosophy, forcing us to ask if we're being observed, what rules govern that observation, or maybe the truth is even stranger. Some theorists suggest we're simply looking for the wrong things. Alien technology might be so advanced it's indistinguishable from natural phenomena. or they've moved beyond physical forms entirely, existing as digital entities in hidden corners of reality. The Fermi Paradox isn't just about aliens, it's a mirror held up to humanity. Are we the first to reach this stage or the last? Is the universe a bustling highway we just can't see, or a silent graveyard of failed civilizations? Every new exoplanet discovery, every silent sweep of a radio telescope brings us no closer to an answer, and that's the paradox's true power. It doesn't just question the cosmos. It questions our place in it, leaving us to wonder, in a universe so vast, is solitude a blessing or the greatest mystery of all? Sometimes the universe doesn't just whisper its mysteries, it nudges us with them. That's precisely what happened with NASA's Pioneer 10 and 11 spacecraft, two trailblazing probes that ventured farther from Earth than any human-made object before them. Launched in the early 1970s, their missions were triumphs of engineering, sending back stunning images of Jupiter and Saturn before sailing into the abyss of interstellar space. But as they drifted beyond the outer planets, something strange happened. Both spacecraft began slowing down slightly more than predicted, as if an invisible hand was gently tugging them backward. This tiny discrepancy, just a fraction of a nanometer per second squared, might sound insignificant, but in the precise world of orbital mechanics, it was glaring. Dubbed the Pioneer Anomaly, this unexplained deceleration baffled scientists for decades. Every conceivable cause was examined and discarded. Was it gravitational pull from unseen objects? The probe's paths were meticulously mapped, and no hidden planets or asteroids lined up with the effect. Could it be fuel leaks or instrument errors? Engineers ruled that both spacecraft were too far apart to experience identical technical glitches. Even the drag of interstellar dust was considered, but the numbers didn't add up. Then came the more radical theories. Some researchers speculated that the anomaly might hint at flaws in our understanding of gravity itself. Could Einstein's theory of relativity need tweaking at the outer edges of the solar system? Others wondered if dark matter was clustering in ways we hadn't anticipated, subtly altering the probe's trajectories. For a time, the Pioneer Anomaly became a rallying cry for physicists exploring alternative models of the universe, a real-world puzzle that seemed to defy conventional explanation. But science has a way of chipping away at even the most stubborn mysteries. In 2012, a team of researchers proposed a surprisingly mundane solution: heat. The Pioneers, powered by radioactive decay, emitted warmth from their electronics and power systems. By meticulously reconstructing how that heat radiated off the spacecraft surfaces, they showed that uneven thermal emission could create just enough recoil to account for the anomaly. It was a painstaking conclusion, requiring years of data analysis and computer modeling. Yet even this explanation hasn't fully closed the case. Some scientists argue the thermal model doesn't perfectly match the observed deceleration, leaving room for doubt and curiosity. The Pioneer Anomaly endures as a lesson in humility, a reminder that sometimes the smallest inconsistencies can point to the biggest questions. Whether it was heat, gravity, or something entirely unforeseen, those two silent probes taught us that the universe still holds secrets in the spaces between the numbers, waiting to be uncovered. And that's the thrill of exploration. Every answer leads to another question, every solved mystery revealing just how much we have yet to learn. Black holes are cosmic enigmas that bend the rules of reality, but nothing challenges our understanding of physics quite like the information paradox. Picture this: according to quantum mechanics, information is indestructible. Every particle, every interaction leaves a trace, like an eternal fingerprint on the universe. Yet black holes, those gravitational monsters, seem to shred this principle to oblivion. When matter falls into one, it's not just crushed out of existence, it's erased from the cosmic record, vanishing without a trace. This contradiction between quantum theory and Einstein's general relativity has sparked one of the fiercest debates in modern physics, a puzzle so profound it's forced scientists to rewrite the rules of reality itself. The heart of the paradox lies in what happens when a black hole evaporates. In the 1970s, Stephen Hawking made a startling prediction: black holes aren't entirely black. They leak energy, now called Hawking radiation, slowly fading away over eons. But here's the catch: that radiation appears random, carrying no information about what fell in. If a black hole vanishes entirely, what happens to all the data it swallowed? Stars, planets, even entire civilizations would leave no mark, violating quantum mechanics' sacred law that information must persist. It's like burning a library and claiming the books never existed. This dilemma has spawned wild and brilliant solutions. One leading idea is the holographic principle, which suggests that all the information swallowed by a black hole isn't lost, it's smeared across its event horizon like a cosmic fingerprint, encoded in 2 dimensions. Imagine a movie projected onto a screen. The 3D world we see might just be a shadow of deeper, hidden data. Another theory proposes that black holes don't vanish completely. Instead, they leave behind tiny remnants, information fossils, holding everything they ever consumed. Yet every answer raises new questions. If information escapes via Hawking radiation, how does it emerge scrambled, like a shredded document reassembled by some quantum origami? Or is our very concept of spacetime flawed, requiring a radical new framework where gravity and quantum mechanics finally reconcile? The stakes couldn't be higher. Solving this paradox might unlock a unified theory of physics, a blueprint of reality itself. What makes the information paradox so thrilling isn't just the science, it's the philosophical upheaval. If black holes can delete information, does the universe have a backspace key? Or are we missing something fundamental, a hidden layer of cosmic logic? Decades after Hawking's revelation, the debate rages on, a testament to how much we still don't understand about the fabric of existence. And until we crack this puzzle, black holes will remain more than just cosmic vacuums. They're the ultimate test of whether our laws of physics can survive the darkest corners of the universe. In October 2017, astronomers in Hawaii spotted something streaking through our solar system that shouldn't have been there, a visitor from another star. Named Oumuamua, Hawaiian for scout, this mysterious object was unlike anything we'd seen before. It wasn't just its interstellar origin that stunned scientists, it was the way it behaved. Most comets or asteroids follow predictable paths shaped by gravity and the sun's pull, but Oumuamua didn't play by those rules. As it raced past the sun, it accelerated slightly, as if pushed by an unseen force. Comets often speed up this way when their ices vaporize, creating a visible tail. Yet Oumuamua showed no such tail, no coma, no obvious signs of outgassing. It was dark, reddish, and eerily silent, leaving researchers scrambling for explanations. Then there was its shape. Based on the way its brightness fluctuated, astronomers concluded Oumuamua wasn't round or lumpy like most space rocks. It was elongated, perhaps 10 times as long as it was wide. Picture a cosmic cigar tumbling through the void. Such extreme proportions are rare in nature, raising eyebrows across the scientific community. Could this be a fragment from a shattered planet? A shard of exotic ice ejected from some distant star system? Or, as a few bold theorists suggested, was it something far more deliberate? Harvard astronomer Avi Loeb famously floated the idea that Oumuamua might be artificial, perhaps a light sail or probe from an advanced civilization. His argument hinged on its unusual acceleration and lack of outgassing. If it wasn't venting gas, what was propelling it? Solar radiation pressure could explain the push, but only if the object were extremely thin and light, like a discarded piece of alien technology. The notion wasn't entirely fringe. Even mainstream astronomers admitted Oumuamua's properties were bizarre enough to warrant consideration of all possibilities, however unconventional. But nature often outpaces imagination. Other scientists proposed Oumuamua could be a hydrogen iceberg, a chunk of frozen hydrogen so pristine it wouldn't leave a visible trail as it vaporized. Or maybe a cosmic dust bunny, a fragile aggregate of interstellar material unlike anything in our solar system. The problem, we'll never know for sure. By the time Oumuamua was detected, it was already speeding away, too distant for detailed follow-up. What lingers isn't just the mystery of one strange object, it's the realization that our solar system might be teeming with interstellar visitors, most too faint or fast for us to notice. Oumuamua was a wake-up call, proving the cosmos is far more dynamic than we imagined. Whether it was a weirdly shaped rock or something even more extraordinary, its brief appearance left an indelible mark on astronomy, reminding us that sometimes the greatest discoveries are the ones that slip away before we can grasp them. There's a map of the universe etched in faint, ancient light, a cosmic snapshot from when everything was just a seething plasma of particles. This is the cosmic microwave background, or CMB, the afterglow of the Big Bang itself. For decades, scientists have studied its minute temperature fluctuations, expecting them to be random, like static on an old television. But in 2005, something stopped them cold. The CMB wasn't just uneven, it was aligned. Not in a subtle way, but along a mysterious axis so pronounced they called it the axis of evil. The name might sound dramatic, but the implications are even wilder. According to the cosmological principle, the universe should look roughly the same in all directions, no preferred axis, no cosmic up or down. Yet the CMB's fluctuations appear to line up along this invisible spine, as if the universe itself has a hidden architecture we weren't meant to see. Some researchers argue it's just a statistical fluke, a trick of the data, but the odds of that are slim, around 1 in 10,000. That's like rolling 100 dice and getting the same number every time. So what could explain this eerie alignment? One theory suggests it's evidence of a gravitational tug from another universe beyond our own, a relic of cosmic inflation's chaotic aftermath. Others propose that spacetime itself might be warped on scales we can barely fathom, twisting the CMB's light like a funhouse mirror over billions of light years. Then there's the unsettling possibility that we're seeing the fingerprints of something even stranger, a pre-Big Bang structure, a scar from whatever existed before time began. The mystery deepens when you consider how this axis eerily aligns with our solar system's plane. It's as if the universe is whispering that we're part of something far larger, a pattern we're only beginning to glimpse. Skeptics counter that our instruments might be picking up contamination dust from the Milky Way, or even subtle errors in data processing. Yet every time scientists account for one potential flaw, the axis of evil stubbornly remains. What makes this conundrum so captivating isn't just the science, it's the philosophical vertigo it induces. If the universe isn't as uniform as we thought, what else have we gotten wrong? Are we living in a cosmic anomaly, or is the axis of evil a signpost to a deeper truth, hidden in plain sight? Until we solve this riddle, one thing's certain: the CMB isn't just a relic of the past. It's a challenge to our future, daring us to rethink the very foundations of reality. We think we know what the universe is made of: protons, neutrons, electrons, the stuff that builds planets, stars, and us. But here's the cosmic twist. Half of that ordinary matter is missing. Not dark matter, not some exotic particle, but the very atoms that should be right under our noses. This is the missing baryon problem, and it's one of the most frustrating gaps in our cosmic inventory. Baryons, the scientific term for ordinary matter, should account for roughly 5% of the universe's total mass and energy. We can tally up the stars, galaxies, and gas clouds we see, but when we add it all together, it's barely half of what our models predict. The numbers don't lie. So where's the rest? The answer might be hiding in plain sight, woven through the vast voids between galaxies in threads so faint they've eluded detection for decades. These aren't just wispy trails of gas. Simulations suggest the missing baryons could be strung across the cosmos in a sprawling web of million-degree plasma, filaments so hot they emit X-rays too soft for most telescopes to catch. Picture a ghostly highway system, invisible to the naked eye, connecting every galaxy in the universe. Occasionally, we get hints of its existence. In 2017, astronomers used the Chandra X-ray Observatory to detect traces of this superheated gas in the space between two distant quasars, like catching a whisper of steam in a pitch-black room. But confirming this theory is like trying to map a city using only the faint glow of its streetlights. The gas is so diffuse, so spread out, that its signal drowns in the cosmic noise. Some researchers have turned to clever workarounds, like studying how these filaments bend the light of distant galaxies, or hunting for subtle temperature shifts in the cosmic microwave background. Others speculate that part of the missing matter might be lurking in rogue planets, black holes, or even undetectable clouds of cold gas drifting between the stars. The real puzzle isn't just where the baryons are, it's why they're so hard to find. If they're truly in these vast, hot filaments, why don't our telescopes see more of them? Could our models be overestimating how much matter exists? Or is the universe playing a trick on us, hiding matter in forms we haven't even imagined? Every time we think we've closed the gap, the numbers slip through our fingers again. What makes this mystery so compelling is its sheer scale. We're not talking about a few stray atoms. This is half the ordinary matter in existence, the building blocks of everything we know, vanishing without a trace. Solving it would mean rewriting the cosmic ledger, filling in a chapter of the universe's story we've only guessed at. Until then, the missing baryons stand as a humbling reminder. Even the most familiar parts of reality can defy our understanding, hiding in the shadows between the stars. The moon today is a quiet, barren world, stripped of the protective magnetic field that blankets our own planet. But pick up a lunar rock brought back by the Apollo missions, and you'll find something astonishing: tiny magnetic signatures locked inside, proof that billions of years ago, the moon had a magnetic field nearly as strong as Earth. This is the moon's magnetic mystery, and it defies everything we know about how planetary magnetism works. Think about it. Earth's magnetic field comes from its churning liquid iron core, a dynamo powered by our planet's immense size and heat. But the moon is just a fraction of Earth's mass, too small, according to conventional models, to sustain that kind of internal engine for long. So how did it manage to generate such a powerful field? And why did it suddenly vanish? The answers might rewrite not just lunar history, but our understanding of magnetism across the cosmos. One leading theory points to a cosmic dance gone wild. Early in the solar system's history, the moon was much closer to Earth, and gravitational forces would have stretched and squeezed its interior like putty. This tidal heating, combined with radioactive decay, might have kept the moon's core molten long enough to spark a temporary dynamo. Imagine a battery that only works when shaken. The moon's magnetism could have flickered to life during these violent tidal interactions, only to fade as it drifted farther from Earth. But there's a catch. Recent simulations suggest tidal heating alone might not explain the field's surprising strength. Some researchers argue the moon's core could have been supercharged by an unexpected ingredient, floating crystals. As the molten core cooled, lightweight minerals might have risen to the top, creating swirling currents that amplified the magnetic field like a celestial amplifier. Others propose a colossal impact, like the one that formed the moon itself, could have disrupted its core in a way that briefly turbocharged its magnetism. Then there's the puzzle of its disappearance. The moon's field didn't just weaken, it collapsed entirely around 1 billion years ago. Did its core simply freeze solid, shutting off the dynamo? Or was there a catastrophic event like a massive asteroid strike that scrambled its internal workings beyond repair? Lunar rocks hold clues, but they're fragments of a story we're still piecing together. What makes this mystery so tantalizing isn't just the lunar angle, it's the bigger picture. If a small, rocky world like the moon once had a strong magnetic field, could other moons or exoplanets harbor similar surprises? Magnetism shields planets from deadly solar radiation, creating safe havens for potential life. Understanding how the moon's field flared and failed could help us spot hidden oases in the cosmos, places where magnetism defies expectations. For now, the moon keeps its secrets. Every new lunar mission, every speck of dust analyzed from its surface, brings us closer to unraveling this ancient enigma. And when we do, we won't just be solving a puzzle about our closest celestial neighbor. We'll be peering into the hidden rules that govern magnetism itself, from the smallest moon to the farthest star. The universe is supposed to be clumpy galaxies huddled in clusters, strung along filaments like beads on a cosmic web. But in the constellation Boötes, there's a place where that rule breaks down completely. Imagine a sphere of nothingness so vast you could drop the Milky Way into it 300,000 times and still have room to spare. This is the Boötes Void, a staggering cosmic desert spanning 330 million light-years, where galaxies are so scarce it feels like someone erased them. Astronomer Robert Kirshner stumbled upon this eerie emptiness in 1981, and to this day, its existence rattles our models of how the universe organizes itself. What makes the Boötes Void so unsettling isn't just its size, it's the sheer defiance of probability. In a universe governed by gravity, matter should attract more matter, leaving few regions truly empty. Yet here, surveys have found only 60 or so galaxies drifting in that colossal void where there should be thousands. It's as if a giant cosmic vacuum cleaner swept through, leaving behind a handful of survivors. Some of those galaxies show strange traits, too isolated and oddly pristine, as if they've been marooned for eons. So how did this void form? One theory suggests it's the ghostly imprint of an ancient collision between smaller voids, merging into one gaping hole in the cosmic web. Another idea points to dark energy, the mysterious force accelerating the universe's expansion, potentially stretching regions of space so thin they become galactic wastelands. But the most tantalizing and controversial explanation involves quantum fluctuations from the Big Bang itself. Tiny imbalances in the early universe's density might have snowballed over billions of years, leaving behind these vast, empty bubbles. Yet even these theories struggle to explain the void's scale. If it formed naturally, why aren't there more like it? And what does its existence say about the rest of the cosmos? Some researchers wonder if the Boötes Void is a fluke, a statistical anomaly in an otherwise structured universe. Others see it as a warning, a hint that our models of cosmic evolution might be missing something fundamental, like invisible forces or undiscovered physics tugging at the fabric of space. Perhaps the most haunting question isn't how the void came to be, but what it means for life. galaxies inside it are so isolated that their stars might never witness another galaxy's light. Imagine civilizations born in those lonely islands, peering into a sky almost devoid of neighbors, their telescopes revealing a universe far emptier than our own. The Boötes Void doesn't just challenge science, it forces us to confront how much of the cosmos might be stranger, lonelier, and more inexplicable than we ever dreamed. And until we unravel its secrets, it stands as a silent monument to the universe's capacity for mystery. Every second, trillions of cosmic rays, tiny charged particles from deep space, rain down on Earth's atmosphere. Most are harmless, low-energy fragments of atoms, but a rare few pack an unimaginable punch. These are ultra-high-energy cosmic rays, barreling through the cosmos with energies millions of times greater than anything our most powerful particle colliders can produce. To put that in perspective, a single one of these subatomic bullets carries the kinetic energy of a baseball thrown at 60 miles per hour, all concentrated into a particle smaller than an atom. The mystery isn't just their power, but their origin. Whatever's launching them must be a cosmic accelerator of almost inconceivable violence, and despite decades of hunting, we still don't know what it is. The search for answers began in 1962, when scientists at the Volcano Ranch Array in New Mexico detected a cosmic ray with an energy so high it defied belief. Dubbed the "Oh my God" particle, it was moving at 99.9% the speed of light, carrying energy equivalent to a brick dropped from waist height, but in a single proton. Since then, we've spotted fewer than 30 of these extreme events, each one a baffling outlier. The biggest problem, physics says they shouldn't exist. At such energies, particles should lose steam as they collide with photons in the cosmic microwave background, a phenomenon called the Greisen-Zatzeping-Kuzmin limit. Yet here they are, screaming through space as if those rules don't apply. So where could they come from? One leading suspect is active galactic nuclei, supermassive black holes at the hearts of distant galaxies, spewing jets of plasma powerful enough to slingshot particles across the universe. Another possibility involves gamma-ray bursts, the universe's most explosive events, capable of accelerating matter to near light speeds in seconds. But here's the catch: when researchers trace the paths of these ultra-high-energy rays backward, many seem to originate from nowhere. Vast, empty regions of intergalactic space with no obvious cosmic powerhouse in sight. This has led to some radical theories. Could magnetic fields spanning millions of light years be focusing and amplifying weaker cosmic rays into these extreme outliers? Or are we seeing the fallout of exotic physics, like decaying super-heavy dark matter particles or defects in spacetime itself? The Pierre Auger Observatory in Argentina, the world's largest cosmic ray detector, has spent years mapping these events, yet the data only deepens the mystery. Some rays appear clustered in ways that hint at undiscovered sources, while others arrive from directions that make no sense at all. What makes this puzzle so thrilling isn't just the science, it's the sheer audacity of the universe. These particles are messengers from the most extreme environments imaginable, carrying secrets we're only beginning to decode. Every time one streaks through our atmosphere, it's a reminder that somewhere out there, nature is running experiments we can't yet replicate, in places we can't yet see. And until we solve this riddle, these ultra-high-energy cosmic rays will keep challenging the limits of our understanding, one unimaginable particle at a time. Most nebulae are cosmic splatters, chaotic swirls of gas and dust painted across the void by the brushstrokes of stellar winds and explosions. But hovering 5,000 light-years away in the constellation Monoceros, there's an exception that stops astronomers mid-scroll: the Red Rectangle Nebula. This isn't just another pretty cloud in space, it's a geometric masterpiece. Its crimson-hued structure so precise it looks drafted by a cosmic architect. Two cone-shaped lobes of glowing gas stretch outward, connected by a series of ladder-like rungs so symmetrical they defy the usual turbulence of stellar death. The central star, a dying sun not unlike our own, should be producing a messy, spherical shell of ejected material. Instead, it's crafting what appears to be a celestial honeycomb. So what's shaping this cosmic artwork? The leading theory involves an unseen companion, a second star locked in a tight orbit with the primary. As the dying star sheds its outer layers, the companion's gravity could be funneling that material into twin jets, sculpting the gas into those iconic conical shapes. The ladder rungs might then be shockwaves rippling through the outflow like rings in a pond. But here's the catch: even with this elegant model, the red rectangle's razor-sharp symmetry remains almost too perfect. Most binary systems create messy, spiral structures, not crisp, angular ones. This has led to some far-out alternatives. Could the nebula's dust grains be unusually shaped, tiny hexagons or platelets aligning like microscopic tiles to reflect light in this bizarre pattern? Laboratory experiments show certain carbon-based molecules can form geometric structures in space, but nothing on this scale. Then there's the elephant in the room, the unnerving resemblance to something engineered. While there's zero evidence for artificial origins, the nebula's X-shape, seen head-on as a rectangle, has fueled wild speculation about megastructures or cosmic beacons. The truth might be even stranger than fiction. Recent observations reveal the red rectangle is rich in complex organic molecules, including anthracene and pyrene building blocks of life. Some scientists suggest the nebula could be a factory for these compounds, its unique geometry creating the perfect conditions for chemistry we don't yet understand. Every new observation peels back another layer, but the core mystery endures. In a universe ruled by chaos, how did nature carve something so meticulously ordered? Perhaps the most humbling thought is this: the red rectangle isn't just a pretty anomaly. It's a challenge to our assumptions about how stars die and how matter behaves in the void. For all our models and simulations, space still holds phenomena that leave us staring at the data, wondering if we're missing a fundamental piece of the puzzle, or if the universe is simply more inventive than we ever imagined. Saturn's North Pole holds a secret so precise it looks like it was drawn with a celestial protractor, a massive, swirling hexagon wider than two Earths. Unlike the chaotic storms we see on Jupiter or the fleeting hurricanes of our own planet, this six-sided behemoth has raged for at least 4 decades, maybe longer. Its razor-sharp edges and geometric perfection defy everything we know about fluid dynamics. On a planet where winds scream at over 300 miles per hour, how does a storm maintain such crisp, angular symmetry? The hexagon was first spotted by NASA Voyager missions in the 1980s, and when the Cassini probe arrived decades later, it was still there, unchanged, as if etched into Saturn's atmosphere. Most planetary storms are turbulent and short-lived, shaped by the chaotic interplay of pressure and rotation. But Saturn's hexagon behaves more like a cosmic gear, turning with eerie precision. One theory suggests it's a standing wave, a pattern locked into place by the planet's rapid rotation and the jet streams that race around its pole. Picture water swirling in a bowl. If you spin it just right, stable patterns emerge. Saturn's version might be a scaled-up, atmospheric version of that experiment, with the hexagon acting like a frozen ripple in its churning skies. But there's a problem. Laboratory simulations can create rough polygonal shapes in spinning fluids, but nothing as stable or as geometrically perfect as Saturn's hexagon. Some researchers propose the planet's deep internal heat plays a role driving convection currents that reinforce the structure. Others wonder if the hexagon is a surface manifestation of something deeper, a hidden symmetry in Saturn's magnetic field or the gravitational tug of its moons. Then there's the wild card. Could this be a rare example of a phenomenon called beta drift, where storms on gas giants naturally organize themselves into geometric shapes under specific conditions? What makes this enigma so mesmerizing isn't just the science, it's the sheer audacity of nature. The hexagon isn't just a weather pattern, it's a lesson in how little we understand about fluid behavior at planetary scales. If something this orderly can emerge from Saturn's chaos, what other surprises might be hiding in the atmospheres of distant worlds? Every new observation peels back another layer, but the hexagon keeps its secrets, spinning silently in the dark, a reminder that even the most familiar laws of physics can twist into something extraordinary when viewed from the right angle. Deep in the fabric of the cosmos, something is pulling, not just a single galaxy or cluster, but thousands of them, all streaming in the same direction at speeds that defy logic. This isn't the gentle drift of cosmic expansion. It's a coordinated march toward some unseen destination, a phenomenon so strange astronomers call it the dark flow. The first hints emerged in 2008 when researchers studying microwave background radiation noticed something off. Galaxy clusters weren't just moving apart as the universe expanded, they were also sliding sideways as if tugged by an invisible hand. The numbers are staggering. These galaxies are racing at nearly 2 million miles per hour toward a point beyond the edge of our observable universe. That's fast enough to cross the Milky Way in just a cosmic blink. What could possibly exert such a pull? The leading theory is as unsettling as it is thrilling. Massive structures lurking beyond our cosmic horizon, so far away their light hasn't had time to reach us since the Big Bang. Picture a mountain range hidden by a distant fog, except in this case, the mountains could be superclusters of galaxies trillions of times more massive than anything we've seen, their gravity warping spacetime across unfathomable distances. But here's where things get even weirder. According to standard cosmology, the universe should be roughly uniform on the largest scales, with no preferred direction or imbalance strong enough to create this kind of flow. The dark flow challenges that assumption, hinting at a cosmos far more lopsided than we thought. Some theorists suggest it might be evidence of a sibling universe brushing against our own during inflation, leaving behind a gravitational imprint. Others propose it's a remnant of quantum fluctuations from the Big Bang itself, frozen into the fabric of spacetime like a cosmic current. Skeptics argue it could all be an illusion, a trick of incomplete data or measurement errors. Yet each new study, like the 2023 analysis of over 1,000 galaxy clusters, only deepens the mystery. The flow persists, its signal too strong to dismiss as noise. If it's real, the implications are profound. We might be seeing the first hints of a reality much larger than our observable bubble, a universe teeming with structures and forces we've yet to imagine. What makes the dark flow so electrifying isn't just the science, it's the philosophical vertigo it induces. Are we living in a cosmic backwater pulled toward some unimaginable attractor? Or is this motion a fleeting echo of the universe's birth, a secret whispered in the language of gravity? Until we peer beyond the horizon, if we ever can, this mysterious drift will remain one of astronomy's greatest puzzles, a silent reminder that the universe's greatest secrets might lie just out of sight. Black holes come in all sizes, from stellar mass remnants of collapsed stars to supermassive beasts anchoring entire galaxies. But in the constellation Monoceros, astronomers have spotted something that shouldn't exist: a black hole so small, so lightweight, it's been nicknamed the unicorn. Tipping the scales at just 3 times the mass of our Sun, this cosmic oddball sits squarely in the mass gap, a theoretical no-man's land between neutron stars and black holes. For decades, scientists thought objects in this range were impossible. The unicorn is here to prove them wrong. What makes this discovery so revolutionary isn't just its size, it's the way it was found. Most black holes reveal themselves through violent outbursts of X-rays as they devour nearby matter, or through gravitational waves when they collide. But the unicorn is quiet, lurking in a binary system with a red giant star. Researchers noticed the giant's light subtly distorting, as if an invisible companion were tugging on it. By mapping these distortions, they pieced together the presence of a black hole so small it defies conventional formation models. Here's the puzzle. When massive stars die, they typically leave behind either a neutron star, a dense remnant no heavier than about 2.5 suns, or a black hole starting around 5 solar masses. The gap in between has long been considered a cosmic dead zone, where stellar collapse shouldn't produce stable objects. The unicorn upends that assumption, forcing us to ask, is this a freak accident, or are countless overlooked mini black holes hiding in plain sight? One tantalizing possibility is that the unicorn represents a new class of compact objects, born from rare stellar deaths where a star's outer layers are stripped away before collapse. Others speculate it could be a primordial black hole, forged in the chaos of the Big Bang itself. Or perhaps our models of stellar evolution need a rewrite, accounting for unknown physics that allows smaller black holes to form under special conditions. The hunt for answers is already underway. Telescopes are scouring the skies for similar systems, while theorists race to simulate how such a lightweight black hole could emerge. Every new candidate discovered or lack thereof will either bolster the unicorn's status as a cosmic outlier or reveal an entire population we've missed. What's at stake isn't just a quirk of astrophysics. If mass gap black holes are common, they could reshape our understanding of stellar life cycles, gravitational wave sources, even the dark matter puzzle. The unicorn isn't just a curiosity, it's a key that might unlock hidden chapters in the universe's story. And until we solve its riddle, this tiny enigma serves as a humbling reminder. Sometimes the most groundbreaking discoveries come in the smallest, most unexpected packages. Beyond the orbit of Neptune, where sunlight is little more than a faint glimmer, lies a cosmic junkyard of ice and rock, the Kuiper Belt. This vast ring of frozen debris stretches billions of miles, home to dwarf planets like Pluto and countless smaller objects left over from the solar system's birth. But there's something strange lurking at its outer edge. Around 50 astronomical units from the Sun, roughly the distance of Pluto's orbit, the number of Kuiper Belt objects doesn't gradually taper off as you'd expect. Instead, it plummets as if someone drew a line in the cosmic sand. This sudden drop, known as the Kuiper Cliff, is one of the solar system's most perplexing boundaries, and it might hold clues to forces we've yet to discover. Picture tossing confetti into the wind normally. You'd expect it to scatter unevenly, with some pieces drifting farther than others. The Kuiper Belt should behave similarly, its icy fragments spreading out in a gradual fade. Yet when astronomers tally objects beyond 50, the numbers crash dramatically. It's as if a cosmic broom swept everything beyond that point into the void. The most obvious explanation, an unseen planet massive enough to clear the area through gravitational nudges over billions of years. This hypothetical world, often called Planet 9, would need to be several times Earth's mass to sculpt such a sharp edge, lurking so far out its escape detection. But the plot thickens. Not all scientists are convinced a hidden planet is the culprit. Some argue the Kuiper Cliff could be a relic of the solar system's violent youth, when gravitational tugs from passing stars or the Milky Way's tides stripped away the outer debris. Others propose that the objects beyond the cliff are simply too dark or too spread out for our telescopes to spot easily. Then there's the wild card. Could this boundary mark the edge of the sun's primordial influence, where the solar wind's push fades into the interstellar medium? The intrigue doesn't stop there. A handful of extreme trans-Neptunian objects, icy bodies like Sedna, and Biden orbit far beyond the cliff in bizarre, elongated paths. Their trajectories seem too stretched to fit standard models, as if something massive yanked them into place. Whether that's Planet 9, a rogue encounter with another star, or a gravitational fingerprint from the sun's birth cluster, no one knows for sure. What makes the Kuiper Cliff so captivating isn't just the mystery, it's the reminder that our solar system story is still being written. Every new survey, every deeper glimpse into the belt's outer reaches could rewrite what we thought we knew. Whether the answer is a hidden world, a cosmic accident, or something even stranger, one thing's certain: the edge of our celestial neighborhood holds secrets we've only begun to unravel. And until we cross that cliff, either with telescopes or someday with spacecraft, it will stand as a silent sentinel, guarding the frontier between the known and the unimaginable. Galaxies aren't supposed to break the rules, at least not like this. Nestled in the constellation Cetus, 65 million light-years away, NGC 1052DF2 isn't just unusual. It's a cosmic rebel flouting one of astronomy's most fundamental beliefs. That dark matter is the invisible glue holding galaxies together. This wispy, ghostly galaxy, nearly as wide as the Milky Way but with only 1% of its stars, should be drowning in dark matter. Instead, when scientists measured its rotation, they found something shocking. It moves as if the mysterious substance isn't there at all. The discovery sent shockwaves through astrophysics. Dark matter isn't just a minor ingredient in galaxies. It's the backbone of cosmic structure, outweighing visible matter 5-to-1. Every galaxy we've studied, from tiny dwarfs to sprawling spirals, shows signs of its gravitational grip except this one. When researchers first published their findings in 2018, skepticism was immediate. Could the measurements be wrong? Maybe the galaxy's stars were arranged in a way that mimicked a dark matter-free system, or perhaps our tools weren't sensitive enough to detect its hidden mass. But follow-up observations only deepened the mystery. The stars in NGC 1052DF2 orbit leisurely, their speeds perfectly matching the pull of visible matter alone. It's like watching a car speed down a highway with no engine. Physics says it shouldn't move, yet there it goes. So how did this galaxy end up breaking the mold? One theory suggests it's a cosmic orphan, born from gas stripped away during a violent encounter with a larger galaxy. Picture a tug of war where one side lets go, the gas, suddenly free, might have collapsed into stars without the usual dark matter scaffolding. Another idea posits that dark matter was somehow ejected, perhaps by a barrage of supernova explosions so intense they blasted it into intergalactic space. Then there's the most radical possibility. What if dark matter isn't as universal as we think? Could there be rare pockets of the cosmos where the rules are different, places where galaxies form through some unknown alternative process? The implications are staggering. If NGC 1052DF2 truly lacks dark matter, it could mean our models of galaxy formation are missing a crucial chapter. Perhaps dark matter isn't always the dominant force, or maybe there are multiple paths to building a galaxy, some with dark matter, some without. This wouldn't just tweak theories, it would force us to reconsider the very framework of modern cosmology. Every new telescope trained on this enigmatic galaxy brings us closer to answers, but for now, it stands as a cosmic question mark, challenging us to rethink what we know about the hidden architecture of the universe. And that's what makes it so thrilling, not just as an anomaly, but as a beacon, reminding us that even the most established truths in science are open to revision when the cosmos decides to show us something new. Quasars are the universe's ultimate lighthouses, blazing beacons so bright they outshine entire galaxies, visible across billions of light years. At their hearts lie supermassive black holes, some weighing billions of times our sun's mass, feasting on gas and dust with such ferocity that the infalling matter glows white-hot. But here's the twist: some of these cosmic monsters flickered to life when the universe was just a cosmic toddler, barely 700 million years old. That shouldn't be possible. According to our best models, black holes that massive need time, lots of it, to grow. They start as smaller seeds, perhaps the remnants of early stars, then slowly bulk up by swallowing gas and merging with others over eons. Yet these ancient quasars, like J034-2915, are already fully grown in an era when the first galaxies were still taking shape. It's like finding a skyscraper in the middle of the Stone Age. How did these black holes get so big, so fast? One radical idea suggests they skipped the usual growth spurt entirely, forming directly from collapsing clouds of primordial gas in the universe's chaotic infancy. Picture a cosmic shortcut. Instead of starting small, these black holes might have been born gargantuan, condensing out of dense pockets of matter before stars even had a chance to form. Another theory points to hyper-efficient feeding, black holes guzzling gas at rates far beyond what we see today, fueled by a universe so rich in raw material that growth happened at breakneck speed. But even these explanations strain the limits of physics. Feeding that fast should create unimaginable turbulence, blasting away the very gas the black hole needs to grow. Then there's the wild card: mergers. In the early universe, galaxies collided frequently, and their central black holes could have slammed together, combining masses in violent cosmic pileups. Simulations show this might explain some of the giants, but not all. The numbers still don't add up. There simply wasn't enough time for enough mergers to build something so colossal. What makes these impossible quasars so electrifying isn't just the mystery of their size, it's what they imply about the universe's early years. Their existence suggests we're missing a chapter in cosmic history, a period when black holes grew under rules we don't yet understand. Some researchers speculate that the first stars, made of pure hydrogen and helium, might have been hundreds of times more massive than today's, collapsing into black hole seeds far larger than anything modern stars could produce. Others wonder if exotic physics, like primordial black holes from the Big Bang itself, could have jump-started the process. Every new quasar discovered in the universe's distant dawn adds another piece to the puzzle, and another headache for theorists. The James Webb Space Telescope, peering deeper into the past than ever before, has already spotted more of these enigmatic objects, their light stretched and reddened by billions of years of cosmic expansion. Each one is a time capsule, holding clues to an era when the rules might have been different, when the universe was young enough to play by its own physics. Until we solve this riddle, these ancient quasars stand as cosmic paradoxes, brilliant, impossible, and utterly defiant. They force us to question not just how black holes grow, but how the universe itself assembled its first structures in the darkness before the stars. And that's the thrill of the hunt. Every answer we find only reveals how much we have yet to learn. The universe is expanding, that much we know, but how fast it's expanding has become one of the most heated debates in modern cosmology. Here's the problem: when scientists measure the expansion rate, known as the Hubble constant, they get different answers depending on which cosmic ruler they use. Some methods, like tracking the flicker of distant stars or the afterglow of the Big Bang, say the universe is growing at one speed. Others, like observing exploding stars in far-off galaxies, insist it's noticeably faster. This discrepancy, dubbed the Hubble Tension, isn't just a minor quirk. It's a full-blown crisis, forcing astronomers to confront an unsettling possibility. Either we're missing something fundamental about the cosmos, or our tools are lying to us in ways we don't yet understand. Take the cosmic microwave background, for example. This ancient light, etched into the sky just 380,000 years after the Big Bang, acts like a frozen snapshot of the infant universe. By analyzing its subtle wrinkles, scientists can calculate how fast space should be stretching today. But when they compare that number to measurements from Type Ia supernova stellar explosions so consistent they're called standard candles, the results diverge by nearly 10%. That might not sound like much, but in the precise world of cosmology, it's a gaping chasm. Imagine two clocks, both built by master watchmakers, ticking at visibly different rates. Either one is broken, or time itself isn't behaving the way we think it should. The stakes couldn't be higher. If the tension is real, not just a fluke or measurement error, it could mean our understanding of dark energy is flawed. Maybe it's not constant, as Einstein once thought, but evolves over time, subtly altering the universe's expansion. Or perhaps dark matter interacts with ordinary matter in ways we haven't accounted for, throwing off our calculations. Some theorists have even proposed wilder solutions, like an undiscovered particle that briefly flooded the early universe with extra radiation, tweaking the cosmic recipe in ways we're only now detecting. Then there's the humbler but equally plausible explanation. We're being fooled by hidden biases in our observations. Could dust be dimming supernova more than we realize, making them seem farther away, and thus the universe faster than they really are? Or are the CMB measurements tripped up by unaccounted-for distortions in the ancient light's journey to us? Teams around the world are racing to cross-check every variable, from the brightness of nearby stars used to calibrate distances to the possible clumpiness of matter in the universe's toddler years. What makes the Hubble tension so electrifying isn't just the science, it's the philosophical weight behind it. This isn't a debate about minor details, it's a reckoning with the very foundations of cosmology. Are we on the verge of discovering new physics, or are we staring at the limits of our own methods? Every new dataset, from the James Webb Space Telescope's razor-sharp infrared gaze to next-generation galaxy surveys, brings us closer to an answer. And when we find it, the implications will ripple far beyond textbooks. The Hubble tension isn't just a puzzle, it's a doorway. And on the other side lies either a revolutionary new chapter in our understanding of the cosmos or a hard lesson in the humility of science. Either way, the universe is daring us to look deeper. From unexplained signals to cosmic anomalies, these 22 celestial conundrums aren't just scientific puzzles, they're invitations. Each one whispers the same exhilarating truth. The universe is stranger, wilder, and more mysterious than we've dared to imagine. Think about that for a moment. Every time we think we've charted the rules, every time we believe we've grasped how things work, the cosmos throws us another curveball, a black hole that shouldn't exist. A galaxy with no dark matter, a void so vast it defies logic. These aren't just gaps in our knowledge, they're doorways to discoveries we haven't even dreamed of yet. What makes these mysteries so thrilling isn't just the what or the how, it's the why. Why does Saturn's Hexagon storm keep its shape against impossible odds? Why does the universe's expansion rate refuse to give us a straight answer? Behind every question lies a deeper story, a thread pulling us toward something fundamental. Maybe the answers will rewrite physics. Maybe they'll reveal forces or phenomena we've never considered. Or maybe, just maybe, they'll lead us to the ultimate humbling realization that the universe isn't just bigger than we know, it's bigger than we can know. That's the beauty of exploration, whether it's through the lens of a telescope, the equations on a chalkboard, or the data streaming from a spacecraft millions of miles away. The hunt for answers is what keeps science alive. And here's the best part, you don't need a lab coat to join in. Every time you look up at the night sky and wonder, every time you read about a new discovery and feel that spark of curiosity, you're part of the journey. So let's keep asking, let's keep pushing, because somewhere out there, hidden in the static of a radio signal or the flicker of a distant star, the next great cosmic revelation is waiting. And who knows, the key to unlocking it might not be in a supercomputer or a space probe, it might just be in the comment section below. Tell us, which of these cosmic mysteries keeps you up at night? Drop your thoughts, hit subscribe, and let's keep unraveling the universe's greatest secrets together. The cosmos isn't done surprising us yet, and neither are we. Until next time, stay curious. The stars have plenty more stories to tell.